Everybody, so welcome to Module 3.2. So in this module here, we're going to continue on with Chapter 2. We're taking a look at load analysis, and in particular, we're going to take a look at some practical applications of tensile testing and hardness testing. So what we're going to do is relate this to some of my past experiences and some of the research and testing that I have done related to the design process. So within this module, what we're going to do is we're going to take a look at some practical applications, some actual designing and machining of parts for some different tensile testing and hardness testing. So with this module here, again, we'll wrap up Chapter 2. Next week, we'll start with Chapter 3. So Chapter 2 had to do with load analysis and some tensile testing. So I'm going to take a look at these practical applications related to my research for some tensile testing and hardness testing. Now, in particular, the test I want to talk about here is a 50 caliber casing test that I did where we're looking at the mechanical properties. Now in this test, the client had given me a couple different cases that they wanted to know the material properties of. A lot of times we're not given too much more information than just that, so we didn't necessarily know what material it was made of. We just needed to run the tests in order to determine what the mechanical properties were. So for the purpose of the preliminary test, we had two different cases that we were looking at that we had to set up for material property testing procedure. So this was just a preliminary test to see how we could do it, how we could set it up, and what we saw. And if the results were favorable from these tests, there was more cases that we're going to need to go ahead and go through and perform these tests on. And what this would do is this would provide us with a method and a testing procedure upon their approval that we could use again for the larger number of cases. Now, there's a couple different reasons why you'd want to run one of these preliminary smaller tests. One of the reasons that we want to do this here was to allow for any of these unforeseen challenges that would arise doing that before we agreed to do a huge, large number of these, or before we committed the time and resources, or the company or client committed those time and resources. We want to make sure that this was something possible that we could do, one, with what resources we had available to us, and two, we wanted to make sure that they saw the results that they were hoping to see out of this in order to proceed forward. Another thing that we can gather from these smaller preliminary tests, another resource that we talk about with these here, is time and money. So if the client only has a certain budget or a certain time frame in which they need these results in, running these initial tests on just a couple cases will give them a good idea of how long it is going to take to set these up, machine them out, run the tests, analyze the data, and get it back to them. And if this doesn't meet their time frame or their budget, it's something they can decide at that point, okay, we're going to stop there after the preliminary test, and that's as far as we're going. But if they do get the results, the amount of time and amount of money it would cost them to go forward with a certain number of cases, they then can proceed and decide, okay, well, based upon that information, we've decided we have time and resources to run 100 cases or whatever it may be for the actual test. So as we proceed forward with the testing, one of the next steps we want to do is establish a test plan and get that approved by the actual client to make sure that it gives them all of the information that they're going to want in a timely manner as well, and that they have all the necessary resources provided to you in order to run that test. So we had a couple test specimens. As we mentioned, we're just going to look at two cases for the preliminary testing here, and these two cases were both non-fired cases, two different types of cases, an LC and a PMJ. And along with that, another thing that we need to note here is we had a control specimen. So this is very, very important here. If we're talking about running hardness tests and tensile testing tests, we want to make sure that our machinery is calibrated correctly. And if we've got two different test specimens that we don't necessarily know what the material properties are or what even we should expect, especially when we're going into this blind as they had wanted us to do, we need to make sure that our system is set up correctly and acquiring the correct calibrated data. So what we do for that there is we create a control specimen. So this specimen is made out of a known material with known properties that we know and we've run before and we know what we should see for results. We could run this as an FEA, we could do the hand calculations, we could look up the material properties on a table, all of that there. So we machine out a specimen of this material here and run it in parallel and actually prior to running the test specimens here to make sure that our machine is calibrated, set up, and ready to go. So after this testing had started, we found a couple things, talked with our client, and then decided to bump up the preliminary test to a total of 4 cases right here and 4 control specimens. So we really wanted to double check every time after each test specimen here and before each test specimen here that everything was calibrated and running correctly, and that we could verify those results from our machine. So we got 4 different control specimens of this aluminum 6160T6, and we also had now 2 of the LC non-fired cases and 2 of the PMG non-fired cases as well. Now this was going to be our initial testing that we were going to perform with this slightly modified preliminary testing case. So now that we had talked to our client, understood exactly what they wanted us to come up with for the results as far as information that they would need for these cases, and we presented them with a test procedure and a testing plan that they had approved and signed off of after some back and forth and revisions. The next step now was to actually create some of these test specimens for this first initial testing. So what we needed to do in order for that was now moving on to the machining process of the design process now. So we worked with the UVM machine shop and a couple other local machine shops for this here, and we were able to do some of this actual machining in-house here. So we had a lot of control, and we could be there and physically watch it and know exactly what we were doing with that there. So we talked about this with the different types of manufacturers before in the design process, where there's different types and different levels of control that you can have over the machining and the manufacturing process here. This one here we had a lot of control over, and we could actually be in the machine shop as they're being machined, double check, make sure the specimens were the right size, make sure everything was correct. This is important for us to, one, get our machining speeds down. We didn't want to work hard on any of the parts there, do the correct lubrication, get the correct sizes and dimensions, make sure we could get the most test specimens out of these. As I can see, these cases are very small for these 50 cal cases. So we needed to order in some special machining bits, figure out special mounts and how we're going to clamp these down in order to do the machining, how we're going to support them, because as we machined out a couple pieces, they were less rigid and less durable, and would start to bend and twist on us while we were machining. So even within the machining process, there was a lot of designing that had to go on there on the fly as we were going through to really figure out how we were going to physically get the test specimens out of these. As you can see here, here's our 4 different cases right there from the unfired rounds. And the next thing we needed to do was machine these dog bone specimens out here. So again, we had 4 different cases here. We called them case A, B, C, and D. Now within each one of these here, we really wanted to get 4 different samples. And the reason we wanted to get 4 different samples is because the thickness of the casing varied as we went up along the side of it. As we varied the distance along the edge of it, that thickness of the casing varied there too. So we wanted to make sure we got as many dog bone specimens as we could at different positions along the case. So this is right here, we have our case sample numbers. So we had A samples 1 through 4, B samples 1 through 4, C 1 through 4, and D 1 through 4. But then we noted next to each of those our distance of the center of the sample from the base of the case. So we wanted to measure where this point is in the center of each of these samples right here in the middle of the dog bone. What was that distance from the end of the case? And with that there, we could then back out what that thickness was of the case along the way as well, which is going to be important when we're talking about doing these tensile testing on dog bone specimens. We need that cross-sectional area right there. So that cross-sectional area is going to be dependent upon that thickness of the material at that point along the case. So as I mentioned before, the machining process itself and just the setup and the actual mounting for these shells in order to machine them was a design process and a challenge within itself there. So we can see what we ended up using is we used a clamp here on the left-hand side in this diagram over here. We used a chuck clamp here from one of the lathes actually that we were able to bring over and implement with a programmable CNC. So how we actually did this, we got a specialized bit down here. So we can see this special mount over here on the left from the chuck, and then we have a special milling bit, which you can see right here, that we had to use to achieve these small dimensions, because we really had to make sure, yes, we were concerned about the inside dimensions, but we couldn't get too far out with the outside. So we needed a very specialized small bit in order to get these small dog bone samples out of the case, and 4 of these small dog bone samples out of each case right here. So you can also see we have coming in here, lubrication was important. We really didn't want to heat this up too much. We really didn't want any work hardening going on. So we also had to really very closely monitor what the temperature of that was, what the speed of the milling bit was, how long it took to machine these. All of that became very, very important because we want these dog bone test specimens and samples to be the same material properties as if they were still in the casing themselves and not a factor of the actual machining to cut those out. So we can see here from another angle, we can see there we have our 50 caliber casing right there, and this is clamped into this chuck mount over here that we've mounted on the side of our CNC. And again, you can see our lubrication coming down here right on this. We can keep this cool and lubricated the entire time through that there. Then we could easily do with this type of mount that we decided to go with here was we could easily then rotate the casing to go to the next dog bone specimen. So within this, again, this is a programmable CNC machine. This is a big, you can see now a zoomed out view here, see how large this actual machine was. Now we were looking at before, there's our little chuck mount right there. There's our 50 cal casing right there. And again, you can see over here on the side, have this little apparatus here so we could rotate this as we're doing machining. And this is a programmable CNC. So what we needed to do was we needed to go in and actually program. You can see a little bit right here of where those dog bone specimens are programmed in now on the CNC machine there. And we'll get into a little bit more of that coding that we needed to do in order to obtain the correct size dog bone specimens for our tensile testing. So with this programming, not only were we programming the specified locations along the case that we talked about for specimen A, B, C, and D for 1, 2, 3, and 4 position, along with the dimensions of the bone, so we are very much concerned with that location dimensions, but also on top of that, in the CNC programming, what we can also specify here is the cutting and tool speeds that are necessary for these cases, again, to avoid work hardening and to make sure that we do this properly and don't change the material properties in the machining process. So the tool speed was optimized in an effort to prevent this work hardening for the test specimens. Also, what I'd mentioned before was we had this specialized machining bit, so we had to order in a 3/32 carbide end mill bit there, and our speed was set within the programming here to 2,000 RPM and a feed rate of 1 inch per minute right there of how fast the tool was actually moving forward. So all three of these were things that needed to be figured out. Now, this is where, when we talk about the different manufacturing options that you have, between full control of the machine shop and more control towards you as the design engineer, the question really becomes, as a design engineer, you really need to ask yourself, how much knowledge and experience do I have as a design engineer with actual manufacturing and machining, as compared to the machinists who could potentially been doing this 20, 30 years for their whole career in the machine shop, where they might already know, okay, this is a brass material, this is something roughly like this, we don't want work hardening, so therefore I have a rough idea of what speeds, feed rates, dimensions, things of that nature, cooling, lubricant I should be using, or do you want to do that research on your own, calculate it, and tell the machinist what to do, or best case scenario, you do your research, figure out what you think is the best, and then work with the machinist who has that experience and collaborate together if that is an option for you. So that's what we ended up doing. I worked with a very, very experienced machinist on here, and my machining skills were nowhere near his knowledge base there. So I took a lot of what he had to say, then went back and did my research as well on top of it to verify that that was okay with our client to proceed with those in a back and forth. So it's not necessarily a one and done type of thing. It's a back and forth conversation between you, the machinist, and the client themselves. So with that information, we were able to program this into our CNC machine for all that information for our location, dimensions, as well as our speeds and feed rate there for our test specimens. So what we ended up doing with this here is we spaced these samples out when they're machined on the cases at 60 degrees apart on the center right there as we rotated around the case. Now, the assumption with that there is that at any distance, set distance from the base, or X distance from the base there for the center of our specimen, that thickness theoretically should be the same all the way around the case. But that's an assumption. So this is where this class differs greatly from what we've seen before in ME12, ME14, where you're given a problem and you're saying, yep, that's an assumption, so therefore we're just going to run with it. That's the thickness of the material. So that's the thickness of the material all the way around. Good enough. We'll run our calculations based off of that. Well, that's not reality. Yes, that case should have theoretically the same dimensions, both the thickness of the case from how it was manufactured and the width of your dog bone specimen that you've programmed into that accurate CNC machine. Great, but reality says not going to happen. Not going to be perfect, especially when we're talking about specimens this small. We really need to measure each individual one. We can't just say this is our cross-sectional area for every single one of these specimens, because that's what it should be. No, we need to actually go in there with some very accurate calipers and measure both the thickness and the width so we can get that cross-sectional area at the center of our dog bone specimen. So that's what we do here. And also to note with that, what's very, very important with all of this is keeping notes, keeping tables, keeping charts, keeping track of everything very accurately and precisely so that you can go back and reference it. So that's what we do here is we say, okay, here's my location. I label my location by where they are and the samples on the specimen. So I have A, B, C, and D for my 4 specimens. And I also have aluminum AL1, AL2, and AL3, and AL4 right there as my calibration piece right there. So therefore, now we have all these different samples here, and for each one of these, I need to know information relative to my dog bone specimen. I need to know the length. It should be 1 inch, but when I measure them, they're not all dead on. 0.997, 0.998. This one's dead on 1, 0.995. So it varies a little bit right there for the length, and that should be dead on because we machined it to be and programmed it in to be 1 inch. Well, there is an accuracy and a tolerance associated with that machine and just machining in general. So we're not quite dead on at 1 inch in every one of these. Actually, only 3 of these were dead on 1 inch when we measured them out to that accuracy. Then the next thing we want to measure was our width. So again, this is something that's programmed in. It should be the same every time. It should be 0.06. Well, 0.059, 0.057, 0.062, not exactly 0.06 every time. So we need to write down what it is. Is that end of the world? No, it's not end of the world, but it needs to be noted and it needs to be figured into your calculations when you're actually running the tests. Then we needed to measure the thickness. And if we think about the shape of a dog bone specimen, there's along that length there, that's a 1 inch length of that dog bone specimen. So I wanted to measure that thickness along that there and see how it varied along that. So not only how it varied between each specimen from those locations, but also how it varied along the length of our dog bone specimen. So I go through and I measure thickness 1, thickness 2, and thickness 3 for each of these dog bone specimens, for each of the test samples that we cut out there, and we note all of these down right there. Then what I say, okay, what is my minimum area? Because if you think about a dog bone specimen, where you're concerned about is that minimal cross-sectional area. Now we've done the shape right and we should be able to do it right in the center of it there, but that's not necessarily the case. So I've measured at 3 different locations along the center of that there, and I have the width. So if I multiply my width by these thicknesses right here, I can get my cross-sectional area, and then what I want to do is take the minimal cross-sectional area for each one of those there, and that is what I'm going to use for my calculations for when I do my tensile testing, is that minimal cross-sectional area. So as you can see, just getting set up into this process here, how much thought, how much engineering, how much design, how much calculation has already been done. We haven't even run the test yet. So we can't even answer anything to our client at this point here. We're just setting up the testing process. So other thing, last column over here is which case this physically is. I know over here for NDA purposes and also for blind study purposes, we label this just A, B, C, D, and aluminum. If this was a blind study, maybe the machinist knows and has this information, or the client knows what this test specimen name over here and how it relates back to the case, so that where the person running the actual tensile tests is blind to that and doesn't have any biases going in and say, oh, I think this case is going to be better than this case, or hold more, and that doesn't influence any of the testing results. So being blind in this is also something to consider when you're running these testing processes, especially if this is a design project that's a passion to you and you want to see it succeed and you believe that it's going to be strong enough, good enough, whatever it is. You don't want that to bias your actual test results. So having a blind study, a blind testing going into something like that is very, very important. So the next thing I want to talk about here are the actual dimensions of these individual test samples, these dog bones that we cut out there. So what I did was I went ahead and modeled this in SolidWorks. Now this is something that I would suggest as well for you guys with your projects that you're going to be running here, is to take advantage of that resource that you have available to you. What I ended up doing was I ended up modeling the entire case, the 50 cal case there, and then I went in and actually machined out or cut out the shape of our dog bone specimen. And I used down here, you can see in the 2D view, this is the shape that I used and programmed in there in order to machine this out. And this is information that is important One, for you to understand exactly what's going to fit in your case. Okay, here's a physical thing, it's curved. How big of a sample can I get out of this without having that radius on the inside of this be an overbearing effect there? How many specimens can I get out of it? And also, this gives you some information that you can then communicate with your machinist or the manufacturer facility for actually cutting these out there. So this has kind of a double benefit there. One, for you to see how many you can get and understand it, and two, to give information to the machinist as he's cutting these out. Now, something to think about here, when you're machining these out in SolidWorks, or cutting these out in SolidWorks, you're basically saying, this is the shape, go ahead, do a cutout or do an extrude around it, whatever it may be that you're using for your process. And when you do that cutout and cutaway, it doesn't really take into account the diameter of the cutting blade, of the cutting bit that we use, at 3/32 one that we specified there. So that's something that we do really want to consider, though, is can you fit that bit in there with the physical shape of the case and the size of the shape and dimensions of that case as well? So that's something there. There are some CAD CAM software programs and some add-ons you could do for SolidWorks where you can physically specify that and go through and do some of the theoretical machining, which is a great opportunity. I know Fusion 360 offers this and a couple other programs as well, which are great. So if you do decide that you want to have a little bit more control over the information you want to give to the machinist in the manufacturing shop as far as speeds, feed rates, milling bits, material types, things like that, that you want to give to them when they're machining it there, then that may be an option as well, to either get an add-in package for the CAD CAM software or use a different resource that has that information as well. If you are going to spend that time and energy doing that, I would double check with the actual machine shop and machinist that you're using, and see if there is a certain software package that they would like the format in, if you're just going to physically hand over a file for them to use, or are you really just going to be handing them 2D CAD drawings like this, and they're going to either program it in or machine it out manually. So things to consider as you're working with your machinist in the manufacturing facility. So now I'm going to take a little bit closer look at these dog bone test specimens that we had machined out of these 50 cal cases. So here's his casing D with the dog bone specimens machined out of it already right there. So we can see over here in this figure here, we have these dog bone specimens machined out at locations 1 and 2. So this is very important as well. One thing I really want you to notice about this slide here is the labeling. So I've labeled things in a couple different places in a couple different manners. So I've labeled this case. I need to know which case this is. So this is case D. Now my specimens are labeled D as well. So I need to know which of these specimens goes with each case precisely. Now, we really don't want to do any engraving because we don't want to damage the structure. We could do some engraving on the actual cases without it being an issue, but on the dog bone specimens, we really don't want to jeopardize the actual material properties of it by doing any engraving on it there. Maybe we could get away with doing the engraving on the grips here, but that was a chance we didn't want to take, so we did use just a permanent Sharpie, permanent black magic marker here to label these here. So we not only did we label what case it came from D, but we also labeled where we cut out each of these here. So this is position 2 on the case. This is the specimen from position 2. This is a specimen from position 1 on the case over here. So we know what case these specimens came out of and what location on that case they're related to. And this is going to be important for us as we move forward, especially if we need to go back and analyze the case, remeasure things, double check things. It's very important we know what specimen it was from, especially in a blind study. If all we know is D and D, we don't know what that is for the case, what that is for the material, any of that information. So with that there, we're actually, I believe I ended up being triple blind in this study, if I recall correctly. I wasn't all told what the material was by the manufacturer at all. They just told, had a cheat sheet where they knew specimen A, B, C, and D were whatever they called these rounds. And then from there, we would just give that information back to them. So we really didn't have any idea. And that's the way they wanted it. They wanted us just to test this and tell us what we found the properties to be. So next step is to set up our actual tensile test. We've gone through, we've set up our procedure, we've machined out the parts. From now, we need to set up our actual tensile testing machine. So what we ended up using here was a smaller one. These are some pretty small dog bone specimens. So the benefit to a smaller testing machine here, we use this test resources system right here. This goes up to 1,000 pounds, and when we did our calculations, that was found to be plenty enough for those dog bone specimens to take it to the loads we needed to take it to for the tests. benefit of this is we could get more accurate results. Rolling up to 1,000-pound load cell right there on the machine, so we could get more accurate results down to smaller loads on the test specimens there, as compared to using a 10,000 or 20,000 pound load cell on one of the larger tensile testing machines there. So we were able to put this in here, and we were also able to fit in, we'll zoom in on it later, an extensometer to get even more accurate displacement results as well for that there. So our next step is to get this all set up, get the hardware set up, get our grips set up, get it calibrated, get the programming set up in here, because we also need to specify for this right here what our feed rate is going to be, how fast we're going to pull this, all of our information. We're going to enter our test specimen size and dimensions into the software here, all that information. So we zoom in here. Now, before we can run this test, again, I'm going to harp on this here, calibration, calibration, calibration. So important. Don't just assume this is perfect. You throw your thing in there, that's the end all be all. No, we need to set this up. It needed to be calibrated, and it needed to be programmed for our specific testing that we were running. So with this here, the displacement, extensometer, and load cell all needed to be recalibrated or recalibrated, even if they said they were before we performed any testing. We wanted to make sure that when it says it went 1 inch or 1.1 inch or 2 microns, whatever the accuracy is, that is accurate. That's truly how far it moved. There's different ways. Sometimes there's calibration plates and distances. Sometimes you can use, on some of the older machines I've used highly accurate calipers and measured the distance between the testing heads. And if I say, okay, it went 1.125 inches on the machine and moved it, does it measure that it moved 1.125 inches? And then for the loads, you may have test specimens of known very accurate, precise loads that you can set on there and different things, 0.5 kilograms, 1 kilogram, 1.5 kilograms. Is it dead on what it says it should be? All of that information is very important. We need to do that calibration before we start our test. Now, once we've completed that calibration in the software, is then going to need to be programmed to write this test procedure. So we've already worked on this test plan, talked over with our client, figured out what we want for all the information, the test rates, is it displacement controlled, is it load controlled, all that information has already been done and specified. Now we just need to program that in order to consistently perform the tensile test on each of the specimens. So when I say consistency, that also means homing. So when we return this back, it re-zeros the load, it re-zeros the distance, it's ready to accept in another test specimen, and we know that it's dead on accurate, so every single test is going to be identical for each of these test specimens that we're going to be using. Now what we decided to do seemed to be the most controllable here was to use displacement control rather than load control or force control. So we then pull each sample at a constant specified rate while recording the information. We could specify what we wanted to record was force and displacement. Oftentimes we record time in this as well just to double check that our rates are accurate there. And then the data was then saved in Excel format. This one gave us the option of a CSV or Excel format that we could save the data in order to post-process it later. Now, again, a lot of the newer machines, and I think even the upgraded software on this machine, did give you the option to program in for each specimen what the dimensions are. And based on those dimensions, you could actually have it calculate your stress and your strain from there and go. But when we took a look at the variations in each test specimen, we couldn't say, okay, every test specimen here is exactly this cross-sectional area with exactly this thickness and width. No, each one varied. So we decided to not use the program for that because it would have been a little bit more to reprogram in every single test specimen into the procedure into the software rather than to just run it and collect force and displacement and then use that information for the cross-sectional area that varied for each specimen in our hand calculations or whatever we choose to actually run the calculations in. I believe I used Excel for that later when we calculated out our stress and strain for that. So the next piece of equipment I want to take a look at here is our extensometer here. So this was attached to our dog bone samples. We can see a close-up down here where we can fit it right in. So this was a challenge here of getting one that would actually fit right in there on our samples right there. It was small enough in width right there that we could do that. And these are slightly adjustable here, so we can move it in to fit it the best we could. We lucked out and were able to find one because the other part was, is it going to fit the clearance this way? Not only does it fit on the specimen itself, but with the ends right here that we're gripping, could we still grip them with enough that they're not going to slip in the grips while still fitting the extensometer in there? And yes, just barely, we were able to do that. Now, this is something that we think about too. I know in a couple of lectures I've mentioned that don't do afterthought design engineering. Think about things again in the brainstorming and design for all of that. So here's a prime example of that. If we would have done our research first and known we needed to use an extensometer for tensile testing, and we knew the clearance between of the actual dimensions of this here, and we wanted to specify this distance here was enough, maybe we would have designed the length of our dog bones a little differently. Luck's out, we were just within tolerance, and this was an existing one that we had in the lab that we could use, and we didn't have to find a specialized custom extensometer or have one made for us. We were able to use that one there, and I believe what we ended up doing was originally these lengths on this were a little bit shorter, and we just changed our programming on the CNC and make it a little bit larger, but just enough to grip onto within our test specimen there. So something to think about as a side note as you're going through, and honestly, no matter how much you plan these out, you are going to have things you're going to need to go back and redesign. We talk about that in the design process, how we stay in a cycle loop as we keep redesigning certain aspects of this moving forward, and that's all part of the process. We try to eliminate as many revisions and keep our time to a minimal, but it is something that is part of the process, is redesigning as we move forward. So data. This is a great topic. Please collect as much data as you can. Keep accurate notes of it. Make sure it's in an organized manner. You know what specimen it's related to. All that information is very, very important. And data collection and organizing your data and data analysis is a huge part of all this here. So after we've done all the testing and it's completed, the raw data had been recorded. So again, we just did force and displacement. We just had raw data there. We imported this into whatever software. I used Excel for this one here and analyzed it for each specimen. So this was based on the load, displacement data, and the geometry of the dog bone. We can see that down here. And again, I did still record the time. There's our load and displacement. Now we can run calculations for stress and strain based upon the information and dimensions that we have there. So I do have even specified columns over here. There's our strain calculation, DL over L for our length right there. There's our stress calculation right here. And from that, we can then calculate out and back out our elastic modulus. So we can get all these material properties that we need, our stress, our strain, our elastic modulus, just off of our load, displacement, and dimensions of our dog bone specimens that we collect there. Again, sometimes your stress and strain could be calculated in the program if you had entered in the physical dimensions, but we opted not to with the variations within each sample that we had there. So this is all in table 3 that we show that data we collected there. We also did this stress strain calculation for our aluminum test specimen right there. So this we come down and we did this for these, so we had a comparison. If we're saying, okay, this is our stress, our strains, our elastic modulus for these specimens, well, is that accurate? I know we've done our calibration, we've recalibrated everything, all the test equipment, but is it correct? We know what our elastic modulus should be for our steel, or for our aluminum 6061, so we can double check it off of that and compare that to what we see for our results for our other specimens as well. So that's a great double check. And again, that's why we did all 4 of these, so we'd have multiple ones of these that we could run with each one of these specimens. So then what I've done over here in this figure here is I've done a graph right here using stress strain data that I created from that load displacement graph readings right there from the test that we did right there. And we can see now we have a typical stress strain graph right here. You can see your elastic region, we can calculate our modulus elasticity, and all those fun things that we would normally see in a stress strain curve we're seeing here. So we can get a lot of information from this graph here for our material properties for each of these test specimens. This right here was for our sample data. I wanted to look at that first because I can look this up. I can find this exact stress strain graph for aluminum 6061 and double check that this is accurate, which one will let us know, first off, is our setup correct? And 2, did we actually have aluminum 6061? And did we have a good specimen of that? Did we have any work hardening with that there? So all that information we can use in order to double check our calibration, double check our test specimen setup for these tests based off of a known material. So relating back to some of our previous lectures that we've seen here, this again is our stress strain data for that aluminum specimen that we have over here for our 6061 aluminum. Now here we go recall what are all these? Well, this is our stress on our Y, this is our strain on our x-axis here. Our Young's modulus for our modulus elasticity is the slope, or our rise over run, where there's our rise going up to our stress on the Y and our run going over our strain in the x direction there. We can back out and calculate our elastic modulus, and we can see right here our yield strength. We can see over here, there's our yield strength right there. Then we can see our strain hardening section from here up to here, where we reach our ultimate strength at the peak right there. There's our ultimate strength right there. Then we have necking occurring all the way down until we hit our fracture, where it fails right there. So being able to relate this back to one of these samples that we've seen. So these are actual results from a real tensile test, and here's what we've seen in our previous lectures for what we should expect to see in a stress strain graph. This is a great comparison, and I think this is a great part of engineering, of seeing everything we've seen in theory, that we've seen in our textbooks and our example problems. Now we're physically running a test, and we can use this information, all this knowledge that we've learned from these courses, for an actual problem that we're solving. Now, if we recall back in this problem here, what we wanted to do was find the mechanical properties of these cases here. So tensile testing was just one method in which we could do that, and coming up with those dog bone specimens, putting them in the tensile testing machine, backing out our elastic modulus out there. Another way that we can do this, and to kind of verify and double check and provide more information on the material properties, is through hardness testing. So this is something you'll also see in your ME124 lab that we're going to do as well. We both do the tensile testing and the hardness testing in ME124 with just samples. But here is an actual physical project that was done for a local company that we worked with, utilizing those methods. So what you're doing in these classes and in your labs is a very practical, valuable resource that you're going to continue on with if you go down the road of design engineering and testing engineering. So with these tensile testing specimens, we cut out the dog bones. With the hardness testing we need to set up, we need to cut out a couple different samples. So what we need to cut out was these rectangular samples, and we're going to use a micro hardness tester. So these were cut to length of the casing from the mouth to the base as much as we physically could. So you can see this is the shape that we cut out right here, right along the case, as close down to the base we get before it came solid there, right up to as far as we could before it kind of angled in up here. And that's what we needed to use, these rectangular samples, for our hardness testing, so we could test the hardness along the entire length of the case. Because if we recall, when we're doing our dog bone specimens, we only got 4 locations along the way for the center of those dog bones along the case. So 4 different areas along that tapered length right here. So it starts thicker down at the bottom, gets narrower as come up here, and with the dog bones you can see we only tested there, and there, wherever those may be. Whereas now on this tensile, or on this hardness testing, we can test on multiple, even more locations along the way for this micro hardness testing. Now what we did here is we machined it so that the top and bottom surfaces were flat and parallel relative to each other. And this is going to be important, as we're going to see coming up here in a few slides, to do our actual testing, to have that flat parallel surface when we're running our micro hardness testing. The geometry would allow for easy setup and good support during the micro hardness testing, which again, this was one of those things that we still needed to do a whole nother design project within this to figure out how we're going to clamp and hold these specimens in accurately to the micro hardness tester with this curved shape of our casing right here. These are not perfectly flat dog bone specimens. They have a curve, concave and convex curve on the inside and outside of these test specimens. And how do we clamp that? Well, keeping that surface parallel so we can come down at a 90 degrees to that with our tip on our hardness tester. So we can see a close up here. We can see we went just as far as we possibly could. And you can even see in this section here how it's a little bit thinner here as compared to here. So if we go all the way back, it's extra thick there. So this changed and varied in thickness all the way from the base to the neck of the case right there. And you can see it along here. Here's your thickness down here at the base. Here's your thickness up here at the neck of this here. And what we want to do is go down through and do micro hardness testing all along this case here at these different thicknesses of the case wall. So this was our hardness tester we used right here. We used a Buhler Micromat 2 micro hardness tester right here. And you can see this is actually a pretty nice, it's an older version, but has a lot of really nice features within this. It sets the load. It has an eyepiece in here that we can use to measure the depressions in it in order to get our data out of it. It has backlighting, has some really precise adjustments here that we can use for moving along the case wall of this here without having to clamp and reclamp and clamp and reclamp at different locations. So this was a great machine to utilize for our hardness testing for this case here. So we zoom in a little bit here. What I ended up having to do in order to get this to fit was to use some parallels. So you can see we have a 1/2 inch parallel down here that this is resting on, and then we also have this hardened steel here that's holding and pressing against this of the inside concave surface of our sample that machined out right there in order to get this to hold and spot correctly. So as I mentioned, this in itself was a little bit of a design process to make sure we got this held and spot rigidly, accurately, and so that these parallels are perfect for what we need to do. So it could rest right on this. The parallel surface of our test specimen could rest right on our parallel that we set down here, 1/2 inch parallel here, and pressed against this with this rod right here. So now we've got this in spot, we can go ahead and proceed with our testing. So a little bit more of a close-up, we can see what we want to do is come down with the tip of our hardness tester right here directly over this length of our parallel right there, which again why we took the time to really make sure when we machine this is perfectly parallel on both sides and perfectly flat for our testing right there. And you can see a little bit more of our test setup right here, holding this, clamping this in spot right there for that shape of our test specimen. So with our hardness testing, we also needed to come up with a testing plan and a procedure that we were going to follow here. So for this hardness testing right here, we use the micro hardness tester, and this utilizes a diamond tip that indents the surface of the sample with a set 1 kilogram load. So again, with this machine right here, this is really nice. It already had the diamond tip, nice and small for what we were using for our very, very small test specimen sample. This is why we couldn't use some of the Rockwell hardness testing machines that you guys have seen in your ME 124 lab that you've viewed right here. We really needed that very small tip to come down to leave the impression and the dent in that surface there. It's really nice that this already is set with a 1 kilogram load. So we know the exact loading of this right here from the machine right there. So the indent left in the sample has a diamond shape to it. So 6 different locations were tested along the length of that there, rather than just the 4 that we saw from our dog bone specimens right there. So we had a couple more locations tested at various thicknesses of the case wall right there. These test locations correspond with the center location of the gauge length of the dog bone specimens plus 2 more right there for the other 6 ones that we did along the way. So what we do here is these are our sample locations that we recall from our dog bone specimens right here for A1, 2, 3, and 4 at these distances 0.9, 1.4, 1.85, and 2.3. So our reasoning for wanting to replicate those was for verification of our results and findings right there. If we can get our material properties at the center of our gauge length from our dog bone specimens from tensile testing, how does that compare to what we see at those locations, that distance away from our base right there, with our hardness testing? Do we see similar results as far as our mechanical properties and material properties go for that there? So those are why we wanted to compare it to the same locations that we did it for our tensile testing specimens as well. So we do that there, and the other 2 locations that I talked about, because we did 6, were on the ends right here. So we did the 4, 1, 2, 3, and 4, which were the locations of our 4 specimens from our dog bone samples. Then we did 1 on each end here, and this is our setup. We're here, a slightly different setup where we had right there, where we're able to come in here and do this vertically and run tests on both ends. Now, because of the shape of this here, what we could do is we could separate these circumferentially from our tensile specimen sample. So we could still go at those same locations, we just rotated around the case, is what we're saying there, a little bit further, a couple degrees more, 10, 20 degrees more when we cut that out. And that we saw when we saw where we machined out the long rectangular specimen that we used for this here. So same distances from the base, but just rotated around at a different location on our case. So as far as our results go for this here, what we can see when we look in our eyepiece right here is we can see this indent on the sample. So we can go in here and we can zoom in. This is actually pretty nice, and we can see there's little crosshairs that are a little bit hard to reference in here. And what we can do is we can measure. We can use these crosshairs as a way of measuring right here the dimensions of this diamond-shaped indent on the and through the eyepiece that we're viewing of our micro hardness sensor. So we could run that, click over, and you can see on this right here, there's individual eyepieces that we can rotate in with different powers that we can zoom in on this here in order to view this and measure it on the micro hardness tester. Now what we can see here is this is pretty small, especially compared to these crosshairs that we're seeing here. So the question is there another way to measure it to double check again and verify that what we're measuring here is accurate for what the actual shape and dimensions of this indent are? So that's where we can use a machine known as an optical comparator that we had in one of our other labs there. And we could see a little bit more zoomed in, better shape of these diamond indents over here. And this is hooked up again to a really accurate stage with a digital readout in this case here that we could then go through and measure, okay, what is this length here? What is this length right here? And get accurate measurements for each of these diamond-shaped indents, and you do this for all of these here and measure from tip to tip there, come across here, measure tip to tip there, and compare these at those different lengths along our cross section of that rectangular shape for that flat machine surface we have there. So the optical comparator was what we ended up using to get more accurate result measurements. And we compare them to what we saw through the eyepiece and the hardness tester. We wanted a little bit more accurate results here with this digital readout, precision digital readout over there. So here's a couple close-ups right here. You can see this is what we saw, and then we can zoom in a little bit further on this here, and we can accurately measure again those dimensions based off of our optical comparator right there and that digital readout. Now, what does that mean for us? So this leads us to a little bit of some calculations we can do here for our Vickers hardness testing here. So based on the dimensions of the indent sample, the hardness can then be calculated here. So we can see this is for a Vickers test here. We know this known force F coming in here. We know the angle of these walls. So based upon that angle right there, we have this relationship that Vickers hardness is equal to 2 times that indent force times the sine of that angle. Now there's 2 of those divided by 2 divided by d squared right here, where d is the mean between these 2 diagonals that we're measuring right there. So we measure tip to tip right there and tip to tip right there. We call that D1 and D2, where D in this formula right here is the average between those two in millimeters. So again, pay attention to your units, just as any of these other problems we've done before. Unit analysis is important. We don't want this in meters. We actually want this in millimeters in order to get our HV or our Vickers hardness of that there. We can simplify this down, do a little math, and we find out HV is equal to 1.854 when we're using this 136 degree diamond tipped tip on our hardness testing machine right there. So we have this relationship right here that we can plug this into in order to get our HVR Vickers hardness for each of those indents. So we go back here, and I want to again go back to reiterating the importance of setting up these charts. So I still have all these samples labeled here. So again, now there's 1, 2, 3, 4, 5, 6 different locations for the samples within each case of this here. And the reason again now for this is because we tested those 2 ends of the casing as well, and not just the 4 locations that correspond to the locations of the center of the gauge length of our dog bones as well. So I have all that information right there, and I have a little conversion factor. I have my calculation again that I've plugged into my Excel spreadsheet to calculate this Vickers hardness out of this right here. So I know I'm going to need to write down all my measurements. So for each of these here, okay, in microns and microns, these are my 2 measurements, which my machine was measuring it in. Convert it to millimeters, because that's what this formula wants for RD, is this is in millimeters there. And then I take an average of this here and use that to plug into this formula right here, which one I tried to plug in, my Excel formula here for that there. And then what I can do is I can convert HV to MPa or GPa by multiplying by these factors right there. So I can go forward now and fill out my entire spreadsheet here with my mechanical properties based on my hardness testing using Vickers hardness right there. So again, I have that known force. That's my 1 kilogram known force. I have my measured distances right there in millimeters, the average of those measured distance. Then from that formula right there that's programmed in, I can then calculate out my Vickers hardness right there. And again, I have my units associated with all these so I don't lose anything. Even in my Excel spreadsheet, I write my units down. Unit analysis is very important, especially with a project like this. You don't want to put it in millimeters or centimeters or instead of microns or whatever it ends up being and swapping it out. That could be very bad for your results. From there are conversions and tables that you can use to go from Vickers to Rockwell and other types of things there. And from that, we can back out our tensile and MPa, convert it to PSA, and from there we can get our yield strength in MPA and PSA as well, based off of some calculations, and we can get that information there and compare it to what we saw in our tensile testing from our dog bone specimen. So we can do a head-to-head comparison between our Vickers hardness testing and our tensile testing right there to verify our mechanical and material properties that we found for these unknown cases where we took our specimens from. So what we want to do is take a look and compare these right now. So if we're just looking at our Vickers hardness right here, we can use our HR values right here, can be approximated from a couple different charts right there, if that's where they wanted to look at those in rather than Vickers. And we can plot this as our hardness versus our distance from the base and see, okay, this is of importance. This is what our client wanted to know is, do the material properties change as we go from the base to the necking, as it goes from thicker to thinner in our walls right there? And what we did find for all four cases, all four of these A, B, C, and D cases that we took the specimens from right there, our hardness did, as we went further away from the base here, our hardness decreased. And we see that in all four cases right there, in all four samples that we tested right there, that was the trend that we saw, that as we went further away from the distance to the base of our case, our hardness decreased.